Next exercise 50. We have a commutative ring here R which is a ring with unity 1 and prime characteristic. We have to prove that if an element A in R is given which is nilpotent, then this equation is true for some positive integer k. That is, some kth power of 1 plus A will be equal to 1. So let's see the solution. So it's given that R has a prime characteristic. So let the characteristic of R be the prime P. What else is given? It's given that A is a nilpotent element. Since A is nilpotent, some nth power of A is equal to 0, wherein is some positive integer. For some positive integer n. Now what we are going to do, we are going to now use the binomial theorem to expand one such power, where in place of k we are going to consider the nth power of p to the power n. And we are able to use the binomial theorem because R is a commutative ring, so the binomial theorem is valid in R. Now by the binomial, what am I writing? Now by the binomial theorem in R, we have, so let's see what we get by expanding this. So if we use the usual binomial theorem, the sum would look like this. The first term is of course going to be 1 plus the binomial coefficient p to the power n, choose 1, times A, plus the next one times A square, and it goes like that, plus at some stage we will come across this times A to the power n minus 1 plus, then of course it still goes on, it's not the end, plus, let me write one more term, and eventually we reach the end of it. Let me write one more term, that is before writing the last one. And then finally plus another term. plus, if you want you can write p to the power n, choose p to the power n, but since that is going to be equal to 1, so we just simply write this. Now here also there is something that I need to explain. I have said that at one stage we will reach n, and then also the terms will continue for some time. But for that to happen, n should be less than p to the power n. Now this fact can be quite easily proved using induction on n. Keep in mind that p is a prime number. So the least value that p can take is p equal to 2. In that case also this is true. And if you have higher values of p, then it is all the more so true. So that's what we have used here. Okay. Now note that this condition is something that we have, which we can apply here immediately. A to the power n of course is 0. This one is also 0. Why? Because it is a times a to the power n. And all the higher powers of a are also similarly going to be 0. So the terms that would survive, once you take that into account, are just these. Now we don't really know whether any lower power of a is also 0, where the exponent is lower than n. That is, say one of these a's, the powers of a may also be 0, because we know from the nilpotency of a that some power of a is 0. Maybe this is not the smallest power, but we cannot claim about these other terms also being, these other powers also being 0. We cannot claim that. However, something else will help us here, and this is where these coefficients play their role. You remember in the previous solution, that is the solution to the previous problem, the 49th one, we proved something like this. Say p is a prime number, then we proved that for any integer I lying between 1 and p minus 1, the binomial coefficient p choose I is divisible by p. Okay, and we used this fact in proving that thing, where we had one such power and we proved in a specific type of ring, we proved that this is equal to this. Now similar arguments can be applied here also, although we do not have p here but some higher power of p depending on what n actually is. But similar arguments show that these binomial coefficients are all divisible by p. So we are going to appeal to that similarity, and I won't show precisely why this is true. In fact, I ask you to go back to the solution to the previous problem, that is 49th one. See how we obtained the result there, that such binomial coefficients are divisible by p, and then come up with your own argument for why these are also divisible by p. It will be similar to that thing. So we are just simply going to write this from, or okay, we cannot write from the previous solution. No? Proceeding like the solution. This also doesn't sound quite right because we are not talking about the entire solution. Instead, let me write like this. Argument similar to the ones in the solution to exercise 1349, and this is the 50th one. Okay, show that P divides this for all integers I satisfying these inequalities. Hence, so now these terms are also going to vanish. Only one will survive. And why is that so? That is because the characteristic of the ring is P. So taking P times something in the ring, which means adding P copies of that thing, is going to get us 0. Although we won't add, for example, here this is a multiple of P, this term does not mean add P copies of a to the power n minus 1, but rather add some multiple of P copies of a to the power n minus 1, but that is also ultimately going to give us 0 because P is the characteristic of the ring. So now we write hence this is equal to this is equal to 1, and that's what we wanted to show. So the k that was being claimed in the actual problem turns out to be P to the power n. And clearly P to the power n is a positive integer because P is a positive integer being a prime and n is also a positive integer. Now let's see the next one. Show that any finite field has order P to the power n, where P is a prime. And hint is also given, which is just an advice. It's not anything specific. Use facts about finite abelian groups. Finite abelian groups. so let's see how this can be proved. It is a very nice result. It says that orders of finite fields are always powers of some single prime. Single prime means for a given finite field, there is some prime for which its order looks like this. If the finite field changes, then the prime may also change. It's nothing fixed. So we start by considering a finite field. Let f be a finite field and let f have k elements. That means let k be the order of f. Okay. Since f is finite, the additive order of the unity, we know that every field has a unity 1, so it will have some additive order, that is order as an element in the additive group of the field. Because the field is finite and hence that additive group is finite, the additive order of the unity element cannot be infinite. Order of the unity 1 cannot be infinite. So that means it's going to be some finite number, some positive integer. Let the additive order of 1 be p. Although the choice of this letter is suggestive, but as yet we are not saying anything about p, that is whether p is a prime or not. We are just simply saying that p is the order of 1, and that means p is some positive integer. That's it. Okay, but now since f is a ring with unity, so theorem what is the number of that theorem? 13.3 or 13.3 implies that the characteristic of f is going to be this p. We know from this theorem that it is the additive order of 1 which determines if the ring has characteristic 0 or finite characteristic. When the additive order of 1 is infinite, then the ring has characteristic 0. Otherwise, it has finite characteristic and its characteristic is equal to the additive order of the unity element. That the characteristic of f is p. Now f is not just any ring with unity. F is in fact an integral domain, and we know that the characteristic of every integral domain is either 0 or a prime number. Because it is not 0, clearly this is a positive integer, so now we can conclude that it is a prime number. Now by theorem 13.4, P is a prime number, and the reason we are able to apply this theorem is that F is an integral domain. So if you want, you can mention that, or you can leave it just like that. We already know that every field is an integral domain. Okay. Fine. So now what is the situation? Now the situation is this. You are looking at this group, and the order of this group is, it's a finite group, the order of this group is k, and 1 of course is an element in this group whose order in this group is p. Additive order means order of 1 as an element in this group. So by corollary to Lagrange's theorem from group theory, we know that P divides K. Okay, so this is what we are now going to write. We will of course not write it this elaborately, we will just simply write the final thing. By, now this conclusion of course does not depend on anything that we have done so far. It just simply depends on the fact that we have that corollary to Lagrange's theorem. By corollary to Lagrange's theorem itself will also have a number, no? Which I forgot to write here. Let me just simply say to Lagrange's theorem from group theory, P divides K. And that's it. That's what I wanted to say. Now P divides K. What is our aim? Our aim is to prove that K is equal to P to the power n for some non-negative integer, actually positive integer n. So simply this divisibility relation is not enough to conclude that. Something else also has to be said, namely that no other prime other than P divides K. Now we need to prove that. What would happen if that is the case? Say, suppose Q divides K as well, where Q is a prime different from P. Q not equal to P is a prime. This is where you are going to use a result from finite abelian groups, namely Cauchy's theorem on finite abelian groups. And that theorem, fortunately I have the number here so that you can go back and see what that is. Since this is a finite abelian, keep in mind that this group is always abelian. In fact, not just in a field, in a ring also, the group under addition is always abelian by definition. Since this is a finite abelian group, it follows from theorem 9.5 that there exists an element, say we call it Y, say, belonging to F, whose additive order is Q. What is the statement of this theorem? It says that if you have a finite abelian group G and Q is some prime number which divides the order of G, then there exists an element in G whose order in the group is equal to Q. That's what we have used here, and that element we are denoting by Y. Okay, so that means we have found an element Y in F which has additive order Q. Because Q is not equal to 1, it is clear that Y is not equal to 0. That's because only the identity element in this group, which is the 0 element, has order 1. Any other element must have order different from 1. Either the order is infinite, in this case that is not possible because the system itself is finite, or the order is some positive integer greater than 1. In any group, the identity element is the only element whose order is 1. So the fact that this order is not 1 tells us that Y is different from 0. Let us mention that fact here. Since Q is greater than 1, we have Y not equal to 0. But what is the other element in this field whose order is P, namely the unity 1, which we already know is also a non-zero element. Since one is also not equal to 0, this violates the result of exercise 47. So you have to recall that exercise. In that, what we proved is that if we are in a commutative ring without zero divisors, then all the non-zero elements have the same additive order. This is obviously a commutative ring without zero divisors because it's a field. And here we have now got two non-zero elements. One of them is 1 and the other is Y. The order of y is q, but the order of 1 is p, and they are different. So the result of this exercise is violated. And that means that this supposition must be wrong. This proves that the last supposition is wrong, i.e. no such prime q exists. That is, no prime other than p can divide k. P is the only prime that divides k. Hence, naturally k will have this structure as a number p to the power n for some positive integer, and that's what we wanted to prove, right? That's it. So this exercise tells us the structure of the order of any finite field. All the orders look like this, powers of some fixed prime. And in fact, there is another result. We will see these things later, hopefully, that for any two fields having the same order, any two finite fields having the same order, they are essentially the same, they are isomorphic. Okay, now let us see another one. Give an example of an infinite integral domain. That has characteristic 3. And it's just a matter of writing one example, that's it. The polynomial ring, this is an integral domain whose characteristic is 3 and which is infinite. Now this of course is a statement that has to be proved, or at least you have to convince yourself that this is true. The fact that this ring is infinite is very easy to prove. these polynomials are all distinct in this ring. These are all distinct elements, because if you apply the definition of equality of two polynomials, no one of them is equal to the other. You can see that. So that means the ring is infinite. Why is the ring, why does the ring have characteristic 3 though? That's because if you add 3 copies of the same polynomial, say you have some polynomial in this ring which looks like this. For some non-negative integer n, where the ai's of course are coming from this field z3 or z3. Now if you calculate this, which is just this, use the definition of addition in this ring, which tells you to add the coefficients of the like terms, you get this. Now, because all of these calculations of the individual coefficients are happening in Z3, and you see 3, that is, here we are adding 3 copies of the same thing. All of them are 0, and that's why your polynomial itself is 0. And this is happening for all the elements in your ring, and 3 is a prime. So that's why this itself is the characteristic of the ring. And why this ring is an integral domain, that also is not very difficult to prove. You already know that this ring has a unity, which is the constant polynomial 1, and you also know that it's a commutative ring. So you just need to show that it has no 0 divisors. And that fact follows from this other fact, that is, if you consider 2 elements here, then the degree of this product is equal to the sum of the degrees, which itself is not also very difficult to prove. You consider this polynomial, you consider another polynomial. So let me do it actually. So g of x is they need not have the same thing here, same n, say bm. Now when you multiply this f of fx and gx, you are of course going to get many terms, but among all such terms there will be one term where you will have this, that is what I am talking about, is this. Now this term, this number n plus m, will not appear in any term. I mean, you multiply out all the terms, all the possible things you do, and then take their sum. That is by definition the multiplication, the product fx times gx. But in all those terms, you never have this, because to get the other terms, you are multiplying terms in which the exponents of x, if you want to call them that, are either less than n or less than m or both. So when you add those numbers, you are never going to get n plus m. You are always going to get something less than that. So that's why when you carry out the multiplication and then you collect like terms, in that process of collecting like terms, this will be left alone. Nothing else is going to come and influence this a n bm. A n bm will remain a n bm. Now, if your original polynomials fx and gx are non-zero, so that there is some largest number n for which the coefficient a n is non-zero. There will be one such if fx is non-zero, and there will be one such if gx is non-zero. And in fact, those things determine the degrees of fx and gx. If n is the largest number for which the coefficient a n is non-zero, then by definition the degree of fx is n. Similarly, if m is the largest number for which among these coefficients bm is non-zero, then the degree of gx is m. Now keep in mind that these coefficient calculations are happening in Z3, which you know is an integral domain. In fact, it's a field, and an and bn are non-zero, bm are non-zero, so their product is also going to be non-zero because we are in a field, we are multiplying things in a field. So an bm is non-zero, and an bm is what? The coefficient of the largest possible term, in the sense that this number is the largest. The others are going to have smaller superscripts there, the other terms, and this itself is non-zero. So by definition the degree of fx gx is n plus m, but n is the degree of fx and m is the degree of gx. So that's how you have this fact. But how can you use this fact to prove that your ring itself is an integral domain? That comes like this. Say you have chosen two non-zero elements here, right? Fx is non-zero and gx is also non-zero. Since they are non-zero polynomials, so their degrees exist. Normally we do not assign any degree to the zero polynomial. In some texts some -1 or minus infinity, some things like that are assigned, but normally we do not assign any degree to the zero polynomial. We do, however, assign degrees to constant polynomials, and that degree is 0. Okay. Now from this formula we know that this is equal to this plus this. So you know that the polynomial fx gx is also non-zero. In fact, this term itself tells you that this is non-zero. That's because this coefficient is non-zero. So you can now say that the product fx gx is non-zero, which tells us that this ring lacks zero divisors, and that's why it's an integral domain. It has the unity 1, it is commutative, and it lacks zero divisor. Okay, now I see that I did not actually need this formula to claim that this has no zero divisor. But anyway, you also came to know about this, or maybe you already know, so we just went through it. We just needed to Multiply these two things out, not fully, but concentrate on this part and show that the product is also non-zero. So there you have the solution. And let me just end things here itself for tonight. We will continue with the other exercises in the next Gallian ring update. And tomorrow, as usual, we have our analysis, where we are, I think, now going to start stating and proving the Riemann's theorem. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.